Hello everyone, today we're going to talk about the method of integrating using trigonometric substitutions. So this is really leveraging all the Pythagorean identities that we can make use of. So let's walk through an example, and then kind of there's a breakdown for based on what kind of algebraic things you see in the problem, which substitution you should make. There's kind of a summary we can do, although sometimes there are little tweaks on those, but let's go ahead and look at an example. So let's go ahead and evaluate the integral from 0 to 3 over 2 of 1 divided by the quantity 9 minus x squared raised to the 3/2 dx. Now this is a pretty complicated looking integral. There's a lot of things going on, and a lot of the standard techniques we have aren't going to be useful here. But you might notice that, well, let me go ahead and just show you the substitution and then watch how everything works out. So let's let x equal 3 times the sine of theta. So the reason you might suspect this is it's going to allow us to kind of simplify that 9 minus x squared. You might see that that could somehow become a Pythagorean identity because, right, if you have 1 minus sine squared, that would turn into cosine squared. So if we do 3 sine of theta, we're going to end up with 9 sine squared theta. So then the 9's will match and we'll be able to pull them out. Anyway, so let's differentiate implicitly. So dx will be 3 cosine of theta d theta. So then we can transform our integral. We also have to look at our limits, changing those over. So again, these are x values, 0 and 3 over 2. So I'll leave that to you to finish those. But anyway, we can see x equals 3 over 2 is going to correspond to theta equals pi over 6. And x equals 0 will also correspond to theta equals 0. So again, you just plug x into the original identity we have here. So 3 over 2 equals 3 sine theta, solve for theta, and 0 equals 3 sine theta, and solve for theta. So then our integral now transforms to the integral from 0 to pi over 6 of 3 cosine theta divided by 9 minus 9 sine squared theta raised to the 3/2 d theta. And furthermore, we can now pull out the 1/9. Well, let's go ahead and simplify first. So let me add a step in there for you. So we're going to go from 0 to pi over 6. So I'll leave the 3 cosine theta alone on top, but the bottom is going to transform to 9 cosine squared theta from the Pythagorean identity raised to the 3/2. And from there, if you take 9 and raise it to the 3/2, you get 27, and cosine squared to the 3/2 is going to be cosine cubed. So our integral just becomes the integral from 0 to pi over 6 of 3 cosine theta over 27 cosine cubed theta d theta. Oh, I wrote a dx in the above line. That should have been a d theta as well. Okay, so now we're just going to be left with 1/9 integral from 0 to pi over 6. And cosine theta over cosine cubed theta simplifies to cosine squared in the denominator. So that is really just secant squared theta d theta. So really that's all we have here is 1/9 times the antiderivative of secant squared is going to be the tangent of theta from 0 to pi over 6. And tangent of pi over 6 is going to be radical 3 over 3, and tangent of 0 is going to be 0, so we get 1/9 times the quantity square root of 3 over 3 minus 0, so we get our final answer of square root of 3 over 27. And again, there's a lot of work that went on in that problem, quite a few steps, but one way that we can always check our answers, this is a definite integral, so we can always go back to Desmos and go ahead and see if the evaluation of the original integral matched what we got doing it by hand. So let's jump over to Desmos just to check that. We ended up with the square root of 3 over 27, and we know that we were integrating from 0 to, I'm just typing in the original integral, 0 to 3/2 of 1 divided by 9 minus x squared to the 3/2 again, dx. And we see that both answers match, so that's good confirmation that we got the correct answer here. So let's go back and talk about the substitutions that we often see here. So actually this is in the textbook, so I'll go ahead and just clip this table in. So let me pause the video for a second and do that. Okay, so here's the table from the book that recommends essentially what we should be substituting. So the previous example, we had 9 minus x squared. So we chose to substitute 3 times the sine of a, which is exactly what we would predict right here. And then we have the identity that corresponds to the appropriate Pythagorean identity. A squared minus a squared sine squared theta equals a squared cosine squared theta. So that's exactly what ended up happening. We replaced 9 minus 9 sine squared theta by 9 cosine squared theta. So we see there's 2 other versions of the Pythagorean identity, and that's where these 2 other versions of the integral are coming from. And you can basically recognize it if we have an a plus x squared and an x squared minus a squared. So we'll go ahead and do a couple of examples that involve both of those integrals, and you'll get an idea for how those substitutions work as well. Okay, so let's move on. So let's do a couple in here. So let's just say, I don't know, evaluate. So for a, we're actually just going to have an indefinite integral. Let's look at the integral of 1 over the quantity 1 plus x squared to the 3/2 dx. So this is a squared plus x squared substitution. So our substitution here should just be x equals the tangent of theta. So let's let x equal the tangent of theta. So that makes dx secant squared theta d theta. So now we have the substitutions we want to make. So we go ahead and write that down. So we're going to have the integral of secant squared theta, and on bottom we're going to have 1 plus tangent squared theta to the 3 over 2 times d theta. And 1 plus tangent squared is going to become secant squared. And then when you have secant squared raised to the 3 over 2, it's going to become secant cubed. So we end up with the integral of secant squared theta over secant cubed theta, which is the integral of 1 over the secant of theta d theta, but the reciprocal of secant theta is just cosine theta. So we are just doing the integral of cosine theta d theta, which is the sine of theta plus a constant of integration. Now, sometimes these are a little bit tricky to go back to our original input variable. For indefinite integrals, we usually want to write them in terms of the variable we started with. In this case, that would be x. So you probably had a couple of these problems in trig, but maybe you forgot about it. Essentially, what was the substitution we made? So let me just make a comment about what we're doing. So changing back to the original variable. what happens is we think about our substitution, which was x is equal to the tangent of theta. Well, the easiest way to think about that is if you had some right triangle and we had theta here, then the tangent is really what? It has to be opposite over adjacent, so that would basically make this side x and this side 1. And then from the Pythagorean theorem, we know the hypotenuse would be the square root of x squared plus 1. So what that means for us is we want to know what the sine of theta would be. Well, the sine of theta would have to be the opposite x divided by the hypotenuse, the square root of x squared plus 1. So if we wanted to write our antiderivative in terms of x, this would actually be x over the square root of x squared plus 1 plus the constant. And that would be it for part A. Okay, so for part C, let's incorporate that last substitution we haven't seen yet, or part B rather. I forgot the first example was on its own. So let's look at another indefinite integral of 1 over the square root of x squared minus 49. And we have a domain thing on this integral. X has to be larger than 7 to make sure that we have a real number in the denominator. So if you go back up to the chart, when you have x squared minus a squared, in this case a would be 7, our substitution is going to be, we want x to be a secant theta, so in this case 7 secant theta. So then dx will be 7 times secant theta tangent theta d theta. Again, there's a domain restriction on this. Typically, this would be for theta in 0 less than or equal to theta less than pi over 2. But this is, we can't include 0 this time because we can't allow 0 in the denominator. So we would just be in the interval 0 to pi over 2. Again, that doesn't really affect us finding the integral, but if you think about the graph of secant of theta and what's going on here, everything makes sense. But that's again highlighted in the table for the substitution. However, I'm just pointing it out because we cannot actually let theta be 0 here. All right, so let's go ahead and transform our integral. So the integral now is going to be 7 secant theta tangent theta on top. And then in the denominator, we're getting the square root of, let's say, what do we have? We have 49 secant squared theta minus 49 d theta. And then what's going to happen? Well, we're going to end up having the square root of tangent squared theta. So I'll include that step just so there's no confusion. So 7 secant theta tangent theta on top, and then on bottom we just end up with the square root of 49 tangent squared theta d theta. So then this actually just becomes the integral of 7 secant theta tangent theta over 7 tangent theta. So the 7's cancel and the tangents cancel, and we're just doing the integral of secant theta d theta. So we did that one in the trigonometric integrals, but if you forgot it, you may just want to look it up. It's a very surprising integral. It's actually the natural log of the absolute value of secant theta plus tangent theta. So if you forget that, I can encourage you to go back and look at it because it's kind of a surprising integral. It's hard to see where it would come from. All right, so if we want to revert back to x's again, what do we have? Well, we have our substitution was x is equal to 7 secant theta, which basically corresponds to x over 7 is equal to 1 over the cosine of theta. So that tells me that 7 over x is the cosine of theta. So my triangle would look something like this. I would have 7, if this were theta, 7 would be the adjacent side, x would be the hypotenuse, and then to find the missing side, that would be the square root of x squared minus 49. So this is again just kind of like scratch work off to the side. But my secant of theta then would still be x over 7, and the tangent would be the opposite, which is the square root of x squared minus 49 over the adjacent, which is 7. So quite an antiderivative on that one. Again, the substitution was straightforward though, and everything just kind of often feels like it works out like magic here with these trigonometric substitutions. All right, so let's look at one last example. This was part B, so C. So one more definite integral. Let's go ahead and integrate the square root of 3 over 3 to 1 of 1 over x squared times the square root of 1 plus x squared dx. So again, this is the substitution where we want to let x be the tangent of x, or x equal the tangent of theta. So basically that means dx is going to be secant squared theta d theta, and also note that the square root of 1 plus tangent squared theta just ends up simplifying to the secant of theta. So we'll do that all in one step. And then also we have our limits. We want to switch those over. So x equals 1 will correspond to theta equals pi over 4. And x equals the square root of 3 over 3 corresponds to theta equals pi over 6. So again, you're just plugging those into the original identity. 1 equals the tangent of theta and solving for theta, and square root of 3 over 3 equals the tangent of theta and solving for theta. Okay, so now we're ready to go ahead and perform the substitution. So our integral is now the integral from pi over 6 to pi over 4, where we have 1 divided by the tangent squared of theta, and then remember the square root of 1 plus tangent squared just becomes secant of theta, and then actually so on top I should have put secant squared, not 1, because that was our implicit. So we have secant squared theta d theta. So we can cancel one of the factors of the secant squared theta. So we end up with the integral from pi over 6 to pi over 4. And we have secant of theta over tangent squared theta. But if we write that in terms of sines and cosines, we can actually make that a little bit cleaner. So what do we have? So secant of theta over tangent of theta is really 1 over the cosine of theta times, all right, tangent squared theta. So cosine squared theta over sine squared theta, which we can actually write as cosine theta over sine squared theta, canceling one of the cosines, which is cosine of theta over sine theta, which is cotangent of theta, and then we have 1 over sine theta left over, which is cosecant of theta. So we can actually rewrite this integral as the integral of pi over 6 to pi over 4 of cotangent theta cosecant theta. And that's useful because we know the antiderivative of that. It's just going to be negative cosecant of theta. So this is negative cosecant of theta from pi over 6 to pi over 4. And so we can figure that one out now. So I'm just going to leave the negative on the outside. The cosecant of pi over 4 is the square root of 2, and the cosecant of pi over 6 is just 2. So if we distribute the negative, we can actually write this as 2 minus the square root of 2. And that is it. So again, these take practice and a little bit of getting used to which substitution goes with which integral. So I would heavily suggest keeping that chart by you in the notes when you're working on these problems. And then again, just more practice with your trigonometric identities. So this is Dr. Lennon signing off.